Hello, everyone. Thank you for coming to my talk. And the goal here is just mostly an ode to the power and an insight that we can get from elegantly simple theoretical population models, and also what happens when you start a project as an undergrad and then keep doing it for over a decade. Okay, and I want to thank my co-authors. Alexander Karatayev, who's my dad, Lars Rodstam, James Watkins, and Luba Burlakova, who's my mom. And so this has been a long, fun collaboration of me trying to teach theory to my field ecology parents as well. Okay, so quagga mussels invaded the Great Lakes on average around 1992. They started out in the nearshore, went offshore, gradually expanding their population size. Okay, so now if you're flying over any of the Great Lakes, except Lake Superior, where it's too acidic to make shells, if you're flying over any of the other Great Lakes and you look down at the very bottom of these lakes, they are completely covered with these invasive quagga mussels. Okay, they now represent more than 98% of all the biomass in these Great Lakes ecosystems. So if you tally up the biomass of all the species in there, 98% of the biomass is going to be these mussels. And their biomass is continuing to grow. So a lot of people are worried about this, partly because these Dreissena mussels are taking the energy that would otherwise, from phytoplankton, that would otherwise go to plankton and fish. They're taking that out and eating it all up, trapping it down in the bottom of the lakes. Okay, so the fish are in trouble, and we're also starting to see indications that they're really controlling the nutrient cycles of these ecosystems as well. So really, really big impacts of just a single species invader. Okay, so we have some really big questions that we're burning to answer. How much algae and nutrients are these mussels consuming and trapping in the bottom? Okay, are things going to get better or worse? It certainly looks like they're getting worse. Do we need to do controlled removals of mussels? Okay, a lot of people are starting to talk about this is going to be extremely hard with the size of these ecosystems. Okay, so what we're really looking for is to measure and forecast the population dynamics, so how these populations will change and how their impacts are changing across this really large landscape, okay, that is the Great Lakes. Okay, and we can't really do experiments in the system at this kind of scale and for long periods of time. Okay, so how can we answer these questions with this dilemma? Well, we have some really cool biology that is rescuing us. Okay, mussels get this kind of constant supply of algae during periods when the water is mixing. Other periods they tend to starve. There's no competition. They don't really have any competitors. Predation is pretty negligible. So this is, and so that means that we can also calculate how much mussels are growing, how much they're consuming and surviving, just from changes in their body size distribution and how their biomass is changing over time. So this is the ideal perfect case for when we can make a population model and make really cool predictions from it. Okay, okay, so we can calculate these important things from changes in body size, and that data is easy to get. We don't need to do experiments. We already actually have this data over the past 2 decades from about 400 sites in 4 lakes. And we just went out and did little, by we, I mean people, not me, do little grabs of the sediment and weigh and measure all the mussels in there. Pretty easy to do. Okay, one of the patterns we see is the length frequency distribution of mussels is changing. Mussels are getting bigger over time, okay, and they're slowly settling down on this kind of central size. The growth is slowing down. We also see no kids, very few small mussels in the population. Okay, the way this looks differs a little bit if you look at different parts of these lakes, but you get the same general trends. Okay, so this is a good opportunity to do one of my favorite things, which is inverse modeling. Okay, we start with data on population dynamics and traits. Okay, we fit a population model to every site that gives us estimates of demography and population dynamics in every habitat. And then we can use existing bioenergetics and nutrient cycle models, which I won't talk about, to make projections of how much algae the mussels are eating and how much they're affecting the nutrients. Okay, so the model is going to be really beautiful and simple. Okay, the abundance of mussels size Y next year depends on how many mussels size X there are this year, times the chance that those mussels survive, and the chance that those mussels grow from size X to size Y in 1 year. And we're going to just sum this up across all current mussel sizes. Okay, our survival is this kind of saturating function. You survive better when you get bigger and your energy reserves are bigger. You starve to death less easily. Okay, and your growth, the bigger you get, the slower you grow. Okay, and this is now the component for birth in this model is a little bit different. Okay, we kind of have this larval reign when it comes to recruitment. Okay, you have mussels all over the lake, they're releasing larvae, and gradually those larvae settle down to any part of the lake, and it's pretty independent of how many mussels are in a location, how many kids you have coming in. Okay, but that follows this kind of Beverton-Holt density dependence, where if there's a high biomass of mussels in a location, all the recruits start starving to death. Okay, and none of them survive. Okay, so we have here 5 parameters that we fit separately for every site, and 2 of them are strongly constrained. Happy to talk about that more. Okay, what kinds of things do these models produce? What kind of dynamics? Okay, you have with high recruitment, these mussels, quagga mussels, make millions and millions of kids each year, of larvae. Okay, they have high recruitment. You blow way past your carrying capacity, and then you have a big bust of population size down towards where the carrying capacity is. Okay, let's look a little bit under the hood with this model in terms of what's going on with body size. Okay, so if you look at size structure over time, okay, at the beginning we have mostly small mussels. These are size structures in the form of heat maps. You have this big pulse of recruits coming in from this massive fecundity. They gradually start growing up. And initially they all survive because there's no competition, but then they gradually start getting bigger, eating out all the food to the point where new larvae coming in, the new kids, starve to death. They can't establish. Okay, and it's only after those that established huge initial cohort, only after they start dying, can you have any more, and the population really starts declining, can you have any new recruits coming in, and new recruits survive and grow in the population. Okay, and so depending on which slice of time you look at, you will see that dominant initial huge cohort slowly getting bigger and bigger, and this is what we see in data. Okay, now these are the results from all lakes combined. Okay, we have biomass here in green and algae consumption here in red. Okay, and what you see across all those lakes is that biomass lags behind algae consumption by 10 to 20 years, depending on which lake you look at. Okay, so what that means is that right now the invader population biomass is still increasing. Okay, we're still reaching the peak of biomass, but algae consumption is already declining. Things look like they're getting worse, but they're actually getting better. Okay, and the other thing to highlight here is that the future declines are really locked in. Okay, these are really inevitable because no kids, we see no kids surviving. We have too many adults, and in most places, like 90% of the population is above its carrying capacity to some extent. Okay, so we're going to see big declines in these populations. Okay, and they tend to be concentrated in shallower areas of these lakes closer to the shore. Okay, that is where we'll see the biggest declines in mussel consumption. Okay, near these shores. Okay, so near shore areas, this is where you have the highest level of algae. Okay, mussel food. Okay, and so if you look at kind of categorize different depths of these lakes, in these near shore habitats, you have higher levels of food, high growth. They grow quickly. They survive moderately well. Okay, and as you go to these offshore habitats, there's low food, slow growth, and high survival because there's no wave stress all the way down there. Okay, I'm omitting really, really shallow areas because that's where there's not enough really bottom substrate that the mussels can attach to, and that's where mortality is really, really high. Okay, and so what we get from this is this kind of trade-off between how fast mussels grow and how long they live. Okay, so in these offshore areas, they grow slowly, live long. In these nearshore areas, you have this perfect combination. Another really key important component of this puzzle is how high mussel recruitment is at different habitats. Okay, so we add the second dimension, and so when we look at the magnitude by which population biomass overshoots carrying capacity, it is really, really high when we have high levels of recruitment and we're in these nearshore, high food, moderate survival habitats. We see really, really large levels of boom and bust here. If longevity is higher with high recruitment, we see lower overshoots and higher levels of biomass. In the other places where we see low recruitment, mussels generally stay at low levels of biomass. Okay, so what this is showing is that fecundity and survival really govern the degree to which an invasive population is going to bust after initially booming. Okay, so this is kind of broad population insights. Also interestingly particularly for mussels, a little bit more broadly, quagga mussels and zebra mussels, they often invade many lakes, and then you go back 2-3 decades later, and it's hard to find these guys. These mussels that were covering these lakes completely, covering the bottom. Okay, so this might help explain why in shallow lakes, mussels often show these population busts. Okay, let's talk a little bit about nutrients. Okay, this group of, I should say, quite talented ecosystem and biogeochemists put together this model of how much phosphorus is in the mussels in the water column. Very lovely, very simple, lovely ODEs. One problem. To parameterize their ODEs, they used data from shallow lakes. Why? Because there was no demographic data on growth and survival available from the Great Lakes that was good to any extent before we did this study. Okay, so we plug in parameters from shallow lakes. Mussels die quickly, they grow quickly. In these shallow productive lakes, we see really high exchange of nutrients between the water column and the mussel tissue. But if you look at where these parameters fall compared to the Great Lakes, it's right here. Okay, really, really, mussels live for 4 years about, and they grow really, really quickly. That is not what we ever see in the Great Lakes. Okay, and so because of this, with our estimates of growth and mortality, we see much less of a much weaker role of mussels in nutrient cycling. It's still strong, but it's not gigantic. Okay, and then we can also, we don't just have point estimates of mortality and mussel growth. We have an entire time series that we can get out of our population dynamical models of mussel growth and mortality. So if we use those time series and force the nutrient models, okay, what we get out of this is that with our empirical estimates of growth and survival, water column phosphorus is starting to recover to sort of towards those pre-mussel invasion levels. Okay, and that is not what the original study found. They're finding less and less, predicting less and less phosphorus in the water column. Okay, so again, things are getting better, and actually find that mussels are now a net source of phosphorus as you have these longer-lived individuals slowly dying. Okay, so where we get parameters for our lovely models is incredibly important. Okay, so this has been kind of really big highlight of a dramatic boom and projected bust of these invasive mussels. Okay, so again, biomass increasing, things look like it's getting worse when actually the impacts on the food web and nutrient cycling of mussels are already declining. Okay, fecundity and survival govern how much invaders bust after booming in abundance. Okay, and we see here that the bust is closest nearest the shore. Okay, so we probably want to focus removal efforts if we ever come to doing them in other places. Okay, and we get all of this by just inferring population dynamics from easily measured traits over time, like body size. And I think that this data was already there. We just put a simple population model to it, and we get these really powerful results. So these are the kinds of things that we're doing in my lab. Thank you.